Let's kind of go ahead and get started here, Ryan. If you want to go ahead and run logistics. First of all, I do want to just briefly say we want to thank Dr. Grant Douglas from CSIRO for being part of this webinar today. And I'll provide a little bit of an introduction for Grant in just a second. But Ryan, if you want to go ahead and give a logistics thing for everybody, that'd be great.
Sure thing, Matt. Thank you. Hey all, my name is Ryan Ingerson. I'm with the National Renewable Energy Laboratory and I help out NAWI with these webinars. A few things before we get started. One, this meeting is being recorded and we will post it online on the NAWI Alliance community website as soon as possible after the event. Usually takes a few days, but we will get that up there. Please note that everyone is joined in listen only mode. This means you will be muted throughout the duration of the presentation, but we definitely want to hear your thoughts and questions. So please insert those into either the Q&A or the chat box. We will be keeping an eye on both and we will address those at the end of the presentation. And if you have any audio issues, please try connecting through your phone. And if that doesn't work, or if you have any other technical issues, please feel free to reach out to me and I will work through those with you. Back to you, Matt.
Great. Thanks a lot, Ryan. All right, so I'm excited today to introduce Dr. Grant Douglas. Dr. Douglas is with the Commonwealth Scientific and Industrial Research Organization, more commonly referred to as CSIRO. Today, he's going to talk about layered double hydroxides, which are interesting in the research community from their application to treat mining and other wastewaters. Dr. Douglas is a senior principal research scientist in Industry Environments Program at CSIRO Environment. And also, as you'll get to see, he's a visiting professor at, it's a School of Molecular and Life Sciences at Curtin University, apologize, and some really cool tools that we got a preview of as we look through this slide deck that will help enhance the presentation that Dr. Douglas is providing. I also like to try to find an interest and a little bit of an interesting tidbit on the speaker. And Grant is strongly embraced technology commercialization, which is something that both Peter and I have. He developed I'm going to assume that's a phosphorus absorbent clay called Phosioc, which is currently used in 25. Phoslock. Oh, I saw it. Well, I need to get my glasses fixed.
Grant, you made Phoslock?
Yep.
I didn't know that. He's famous, Matt.
Yeah. I pronounced it wrong.
Dude.
How do that was my way. That was the way I was going to do it.
It's a lanthanum thing. Yeah. Phoslock's the bomb. Yeah.
So all this cool
about
things.
Grant. Wow.
See, you guys could share the entrepreneurial bug here,
awesome.
You know. So Grant, why don't you go ahead and take it away? Thanks again for being here. And like I said, like Ryan said, if you have questions, chat or
put them in during the chat
as
they come to you. Yeah, we'll talk to all about that at the end. All right, off to you, Grant.
Okay, thank you very much. I'll just share my screen here and hopefully you will be able to see that. I go to presentation mode. You can see that?
Switch it. It's got the it needs to, okay. It's got the notes one.
Notes one. Okay. So what I will do is stop share, and then I will have to just bear with me one moment.
Okay.
Okay. So I have to go back over to there, I think. All right. And share screen. And I'll do screen 2.
There, let's see.
You can see that.
Okay. And it's coming through. Bingo. Okay, that's it. So you're on one of your later slides, but you've got it. All right. Okay. Go ahead. Take it away.
All right. Thank you very much. Well, it's a good morning from Australia and a good afternoon to everyone else in the US. And as advertised, I'll be talking about layered double hydroxides and their applications in really cleaning a whole lot of things up from contaminated waters. And as you see on that top slide there, oh, sorry, the top image there, this is actually something you'll see a little bit later, but it's a novel uranium rare earth mineral that we were able to form as a result of using the layered double hydroxides to clean up a uranium-rich groundwater. I should also say that we were recently awarded a NAWI project, and this is ultra high pressure CSIRO with virtual curtain being the commercial name of this in situ layered double hydroxide technology. And that's used to achieve mineral liquid discharge. And I'll talk a little bit about that right near the end of the presentation. So we'll start off now with what are layered double hydroxides? Well, the naturally occurring and synthetic minerals. The layered double hydroxide, or LDH, which I'll use as an abbreviation here, is a sandwich structure. So it's a bit like normal clay minerals where you have two layers. In this case, though, they're positively charged metal hydroxide layers, and then you balance the charge with a range of interstitial ions, and you also have waters of hydration. Luckily, there's a broad compositional range for layered double hydroxides. So you'll have anything from say a 2:1 to 4:1 M2+, a metal 2+ to metal 3+ ratio. And there's a couple of formulas there. The first one being a 2:1, where you've got Mg4 to Al2, and then Mg8 to Al2 is your 4:1 ratio. Now, a really fortuitous characteristics of layered double hydroxides is that you're able to substitute a whole range of metals into them. So for the M2+, you've got your typical suspects there, so magnesium, calcium, copper, zinc, and a whole range of others. And for your M3+, your Al, iron, rare earth elements, again, a whole lot of others. And for your anions, you can have monovalent, divalent, trivalent anions, and again, things like sulfate, bicarbonate, carbonate, and the like. And one of the really fortuitous outcomes of when you actually make in situ layered double hydroxides as opposed to ex situ ones that you add, for instance, to a contaminated water, is that you're able to use these contaminants as a building block in the layered double hydroxide. So you can form what I've termed here polymetallic layered double hydroxide. So they can be a whole range or a whole mix of both anions and cations in the structure. And so I've said there in the last point, the layered double hydroxides then constitute a multi-element contaminant repository. So again, I talked about that sandwich structure, and you can see on the left-hand side there, we've got the sandwich structure of the prisms there. We've got the bluish prisms, or maybe purple prisms there, which might be your metal 2+, and then interspersed with those, you've got your 3+, so things like iron. You've got then a net positive charge, and in between those layers, you've got those green golf balls there, which can be your anions, and then your waters of hydration are those little red and white elbows. So what does that look like in practice? Well, here's actually some in situ layered double hydroxides we produce from a uranium mine groundwater, which I'll talk about a little bit later. But I've termed these as botryoids, almost look like bunches of grapes. And then when you actually have a look at those in higher magnification, you've got the scale bar there of 200 nanometers, you can actually see the layered double hydroxides face to face and face to edge and so forth. If you look at the little one, the actual edge that you can see edge on there near the 200 nanometers, just to the left of the 200 nanometer scale bar, that's around about, say, 20 nanometers thick. Now, you've got a typical basal spacing in a layered double hydroxide between about 1 and 1.5 nanometers. So you're probably looking then at around about, say, 15 to 20 layers thick in that layered double hydroxide that we've got there. So just a little bit of an insight of what they actually look like once we form them. So, why do we make them? Also, what are the advantages of making them, and particularly making them in situ? Well, as you would have gathered from the previous slides, we get a broad spectrum contaminant removal during in situ precipitation. As you'll see later on, we can get very high concentration factors. I've said 100 to 500 times here, and it very much is a function of the actual wastewater that you're treating. you get very rapid formation. Once the conditions are right, the formation is instantaneous, and you also get extremely good settling, and I'll talk about that in a moment as well. Another really good fortuitous characteristic is it promotes in-train aggregation and of particulate materials. So you actually get, once you form these LDH instantaneously, they'll actually form bridges between colloids and particulates. And so you can actually clarify turbid waters. And that's really, really useful, that you've got something that takes out a whole lot of metals, but you can actually also take out a lot of the turbidity and on occasion some of the dissolved organic carbon. One of the other really good characteristics again is you can use it for these from fresh to saline to hypersaline waters, and I'll give a few examples, as I will, of low to high pH waters where these have been used. The layered double hydroxide precipitation can also near quantitatively remove a whole lot of elements there, and these are typical foulant elements that you'll be familiar with in RO. And so what we get is a simplified post-treatment solute composition. So we've removed all of our foulants, and that can only mean good things in terms of enhanced RO performance. So what I'll talk about now is 4 studies that we've actually undertaken with these layered double hydroxides. The first one being an in situ batch treatment of acid mine drainage, and that's low pH, low salinity, and a whole range of major and trace elements, including indium, which I think in 35 odd years of work, I'd only once ever come across indium before. And in fact, we were able to remove indium from this particular contaminated water. I'll also talk about an in situ pump and treat method for reduction of total hardness and silica in a groundwater, so circumneutral pH and low salinity. I'll then talk a bit about a treatment of a uranium, what's known as ISR, or in situ recovery mine, so low pH and high to hypersaline salinity, and a whole lot of major and trace elements, but in particular here also radionuclides. And it's very important that we can demonstrate that we can take out a whole range of radionuclides as well as major and trace elements. And then building on that, I'll look at the thermal conversion or amorphization of these radionuclide enriched layered double hydroxides into a potential nuclear repository material. So the first one, this is in situ acid mine drainage treatment, and this is from a mine called Balgammon, which is located in far north Queensland, if you know Queensland on the Pacific coast. As I said, this involves in situ layered double hydroxide formation. This was treating 56 megalitres, which I think is about 15 million gallons of acidic, copper and zinc and other metal contaminated water. Now in this, to get the actual M2 plus to M3 plus ratio that we needed, we're aiming for a ratio of 3, remembering we have a 2 to 4 range. We needed to add magnesium chloride, and in the top left slide you can see that we've got, if you look really hard, we've got a circular image there on the top of the pit. That's actually a sprinkler on a pontoon where we're irrigating the pit with the magnesium chloride. You can actually see 2 different colors: the green where we've added the magnesium chloride and we're forming copper chloride, and the bluish areas that we were yet to treat, and that's still the copper sulfate, so that blue versus the green color. Now, what we did after that was we added sodium hydroxide and we took that up to final pH. Once we did that, we had spontaneous formation of the layered double hydroxide. And with that spontaneous formation, it immediately began to self-aggregate and settle. And from a pit that we couldn't see the bottom of overnight, all the layered double hydroxides had settled without the aid of flocculant or anything else. They had settled the 9 meters, and we could actually go out to the center of the pit and see the bottom. So then if you look at the right-hand image there, that's the actual layered double hydroxide. You can see it forms pretty much an amorphous-like gel structure. And then if you go to the bottom left slide there, you can actually see what it looks like on the bottom of the pit. So we were then able to treat that water with reverse osmosis and discharge that water over the side of the pit. One of the other important things was that we had the initial concentrations of copper and zinc were 40 and 20 milligrams per litre respectively, but with those high concentration factors that I talked about, we're actually able to form an ore grade layered double hydroxide. There's in fact about twice the ore grade of the pit that they were mining. So we had about 8% copper and about 4% zinc. And so that opens up the possibility then of being able to reprocess that layered double hydroxide and actually get metal values out of it to offset some of those treatment costs. Okay, so now if we look at the composition of the water pre-treatment, post-treatment and post-RO. So pre-treatment, pH was around about 2.9, post-treatment about 8.5, and post-RO about 7. Now, I won't go through every element there, but if we just look at the bottom box there, where we have things like AL, where we went from 70 to 0.06 after the layered double hydroxide treatment. Similar reductions, or very large reductions for all those obviously in the red, which are all below detection limits. And we have silica as well. They're one of the major foulants, going from 60 milligrams per litre down to 1.3. So really, as I tried to emphasise earlier on, a broad spectrum removal of a whole range of contaminants of quite widely different chemistries. And as I alluded to earlier, we had foulant removal, so all of those usual suspects in terms of foulants, and that really did give us very much enhanced RO performance. The RO was able to breathe effectively. So the treatment of this pit was completed in about 20 days. So that was both formation of the in situ layered double hydroxide and the RO. The other important thing was the final sludge volume and the RO reject volume was around about 5 megalitres. And so that meant that we were able to discharge over 92% of the water to the local environment within 20 days. So that's really, quite phenomenal that we're able to get in and treat what is a really, really nasty lot of acid mine drainage water and treat that and discharge it within 20 days. Okay, I'd like to move on now to the second example of the application of layered double hydroxide. This is a Chinese coal industry groundwater. This is a coal industry gasification plant where they convert ethane gas into polyethylene for water bottles and the like in China. And the requirement here was to treat 800 cubic meters an hour, or around about 7 gigalitres a year. So that is a heck of a lot of water. And so this was a pump and treat system. So the groundwater was pumped up out of the ground. We then retrofitted this system where we had sequential injection of the reagents. In this case, it was only 2 reagents that were injected. You'd inject one, have an in-pipe mixer, inject the second, again, have another in-pipe mixer or static mixer. So very, very simple. And then what we had was the neoformed, what we had was the neoformed layered double hydroxide. They were able to capture it in a sand depth filter. And so that was a really efficient and quick way that we could actually treat this water. And on the right-hand side there, we've got in the top image, the silica. So we've got silica in the blue and 2 streams of silica out of the system. And you can see the silica in was, say, anywhere between, say, 60 and 80 milligrams per litre. The silica out was probably around about 20 milligrams per litre. And if you have a look at the total hardness, well, that's quite variable, but let's just say it's anywhere between 600 and 1,000 coming in. And over time in the outlets, it's probably anywhere between about 200, and it rose over time as it did in the inlet concentration to say 400 or 500 milligrams per litre. One of the other things I want to emphasise, though, were 3 forms of silica were also captured. We're able to capture the monomeric silica, we're able to capture the polymeric silica, and also the colloidal, and that's through that aggregation process. So that's where we actually get, again, a broad spectrum of different silica types as well as the total hardness. So what did we get in terms of performance? Well, turbidity was removed or reduced by about 85%. We had around about a 60% reduction in total hardness, and the constituents there, calcium and magnesium, were removed by a similar amount. And we had about a 66% removal in silica. But collectively, that total hardness and silica removal actually gave us around about, or gave the plant operator around about a 50% increase in RO efficiency. And that was absolutely a fraction of the cost that it would take to build that additional RO plant capacity at site. And the other thing is that they had some softening columns, some ion exchange softening columns at the start of the process. And following the in situ layered double hydroxide treatment, they were able to reduce those from 3 to 1 operational ion exchange column. Now, we were actually getting much better reductions in both total hardness and silica in some of the lab trials. And I think we actually could have done even better in the field. The implementation wasn't fantastic, not what I wanted to see. But nonetheless, it still is, I think, a very nice demonstration of the capacity of in situ layered double hydroxides to remove both silica and total hardness. But there's a lot more work to do in this area, I should also say. Okay, I'd like to move now on to looking at radionuclide capture and containment. And as I alluded to earlier on, this is the Beverley in situ recovery uranium mine in South Australia. And there's a little image of South Australia and where this mine is located, a few hundred miles north of the capital city of Adelaide. As I said, this is an in situ recovery mine. In this case, they pump what's known as a lixiviant, which is effectively an acid and an oxidant, into a well field. And you can see the images of those well fields on the two right-hand images, both the top and the bottom. And putting that acid and the oxidant in, they're able to recover uranium. But what also happens is when you dissolve up the uranium, you also dissolve up a whole range of the daughter radionuclides and a whole range of other contaminants that are associated with the uranium mineralization. So what's known as now the pregnant lixiviant, which is full of uranium, is pumped up to the surface. They then use ion exchange to form a barren lixiviant. Now, this barren lixiviant is then refortified, and it's used over and over and over again, being pumped into the aquifer to recover more and more uranium. But each time, you then begin to build up a quite substantial burden in terms of radionuclides and other trace elements or contaminants. But what this formed for us was what I've called there a convenient workhorse solute. Because given the uranium in it, but also the amount of daughter radionuclides, it formed what we sort of like to term as a nuclear analog for the research that we conducted. So what actually happens when you form a layered double hydroxide from this barren lixiviant, which, as I said there, contains uranium, a whole range of elements, including radionuclides, it's acidic, and it's saline. What I've got on the right-hand side there in that image is a pH versus moles of base added plots. And you've got the pH in the blue, and you've got dpH, the volume of moles of base added there as well. So you can actually better see some of the inflection points. So there are 5 main processes. I should actually point out the magnesium was added as well in this to give us our magnesium, our metal 2+ to 3+ ratio, again of 3. And again, we titrated sodium hydroxide as our base to an endpoint. So there are 5 major processes here during formation. pH 3 to 4, no surprises. You start to precipitate out your iron hydroxide as you increase the pH. You start to precipitate out your Al hydroxide. As you increase the pH, though, in this case from 7 up until 9, you actually start to redissolve that Al hydroxide up into the aluminate ion. And then once you get to higher pHs, up to 9 and above, you start to form brucite, which is magnesium hydroxide. Now that's really important. So we've now got magnesium hydroxide and we've got the aluminate anion. And when you have those together, you get the spontaneous self-assembly of those, plus other cations, anions, and radionuclides into the layered double hydroxide here. Here, as I said, a 3 to 1, Mg6 to Al2 layered double hydroxide. Now, the other thing to note here is that the mass of this was around about 3 grams per litre, or about 0.3% by mass. You really are getting very small amounts of the layered double hydroxide. And again, that attests to the very high uptake capacity and the concentration factor that we've seen previously in the Balgammon mine pit, and we'll see in a few moments here. So if we look at this now in a different way, and this takes a little bit of understanding, but we've got a ternary diagram here on the right. We've got magnesium up the top, iron on the lower right, and Al on the lower left. Now, if you look on that ternary diagram, we have the initial barren lixiviant there in the blue diamond down near the bottom. And once we've added the magnesium to it, we have the red dot. And that red dot sits within a pale blue area, which is effectively the stability field for layered double hydroxides within this magnesium, iron, alumina ternary space. So what happens when we start adding hydroxide? Well, if we start at that red point and we follow the green line around, as we start adding hydroxide, we get to pH 3.1. And so the composition of that precipitate, as I talked about before, is iron rich. So we move towards that iron apex. As we start then increasing the pH again, we get down to 4.4 and then 5.2 up to 7.3. We're starting to add Al into that. So we then start to move from towards the iron towards the alumina apex. So now we've got an iron and alumina precipitate. Then once we start increasing the pH above 7.3 through to 8.1 through to 9 and then up to 10, as you saw previously, we start adding magnesium that starts to precipitate out, and we end back up pretty much where we started. So we've precipitated everything out in terms of the magnesium, the aluminium, and the iron. And you can see all those little open dots there. They're SEM point analysis, and they confirm the final layered double hydroxide composition, which is pretty close to where we actually started. So job completed, that's what we wanted to see. If you look at the pink line now, again, we start at that point where we had the layered double hydroxide composition after the magnesium was added. As you look at that pink line, the solute composition starts to move away from the iron, again, because now you're depleting the solute with iron, and then starts to move away from the aluminium after pH 4.4. And as you move up to pH 10, you've depleted all the aluminium, you've depleted all the iron, and then you've got a small amount of magnesium occurring in the final solute. So this is just a really nice way to look at the behavior and the composition of both the solid and the solute as you form the layered double hydroxide. And thankfully, we end up with a final composition that's pretty similar to where we started and what we wanted to form. Okay, if we have a look at now layered double hydroxide removal efficiency for a whole range of elements. So we've got, I should point out first on the y-axis, this is the ratio of the barren lixiviant, so the untreated lixiviant to the treated lixiviant, so the contaminated to the decontaminated. And we've got a whole range of ratios there, everything from pretty much a ratio of 1 through to a ratio up to almost a 1 million times in terms of the ratio of dirty to clean, effectively. And on the x-axis there, what we've got, I've ranked the elements according to their removal efficiency, and I'll talk about that now. So we have 4 natural groupings there that actually fell out of this. The first grouping contains uranium, and we had about 1% uranium in this layered double hydroxide precipitate, around about 2.5% rare earths. And then we also had thorium, iron, and aluminium. So if you look now at that x-axis, you can see a whole lot of rare earths, cerium, neodymium, lanthanum, praseodymium, and the like. We can also see thorium, uranium, and also a couple of trace elements in there, things like cobalt and cadmium, as well as the Al. But predominantly uranium and rare earths and thorium and aluminium and iron. The second natural grouping there is a whole lot of transition metals and metalloids. In fact, what I should do is just go back quickly and say that the concentration factors there for those rare earths, uranium and the like, anywhere between about 1,000 times and about 200,000 times. So the enormous removal efficiencies compared to the original barren lixiviant. We look now at the second grouping, and this contains predominantly transition metals and metalloids. So we've got silica in there, we've got zinc, and you can scan across, you can see copper, you can see nickel, thallium and the like, and even down through magnesium and fluoride. And those concentration factors are anywhere, depletion factors, I keep on saying concentration, depletion factors of the barren lixiviant over the treated lixiviant, anywhere between about 2 times up to about 100 times. The next group are the alkalis and alkaline earths. And they're pretty much at anywhere between about 1 and 2 times in terms of the depletion factors. In some way, who cares? They're just alkalis and alkaline earths. We didn't really do much in terms of removing the salts from this hypersaline water, and that was never the aim. It was always about removing things like radionuclides and trace elements. And the last grouping there is what we had a net addition to. So they fell below that 1 ratio line. So we had some chloride because we added some magnesium chloride. We had sodium because we added sodium hydroxide, and we added a bit of bicarbonate. Again, who cares? We added some NaCl and we added a bit of bicarbonate to the system. Now, if we look at the radionuclide removal, and again, another really interesting story, that in summary, we remove anywhere between about 92 and about 99.9% of the uranium-thorium decay chain radionuclides. I've got the uranium decay chain there on the right, and all of those circled either in the green or the red are the particular parts of the decay chain that we looked at. And if you look at the radionuclides, down in the table there in the first line, so we've got everything from uranium-238 at the top of the chain to lead-210 at the bottom. We've got the activity now in becquerels per litre in the second column of the barren lixiviant. Then we've got the treated lixiviant activities in becquerels per litre. As I said, the percent removal. So as I said earlier, anywhere between about 92 and about 99.9%. And then within the layered double hydroxide precipitate, we have the activity in becquerels per gram. So some very large activities, particularly there for thorium-230. Almost 2 million becquerels per gram, but aggregated, we had a radionuclide enrichment of around about 2.8 million becquerels per gram. So this is a really, really efficient getter for a whole range of radionuclides from the uranium and in fact thorium decay chains as well. And that's one of the really, really good outcomes of this research, is that we were able to demonstrate that we were so efficient in actually removing a whole range of radionuclides. And this just, now we're looking at some other work we did on the synchrotron using XAFs. And this was a study using both synthetic and barren lixiviant and in CO2 rich and CO2 poor systems. Now, all I really want to talk about in this slide is that we were able to show that rather than uranium being accommodated within the metal hydroxide layers per se, they were actually all accommodated on the edges. And those edge complexations often involve the carbonate or bicarbonate molecules, and they actually form then polydentate ligands at the edges. So it was very much a ligand exchange mechanism on the edge, and that resulted in the formation of these inner sphere surface complexes. Now, the really important finding out of that is that if uranium is last on when we form these in situ layered double hydroxides, it's also likely to be first off. And that's important if you're thinking about, well, can we actually recover uranium from these in situ formed layered double hydroxides? And that, in fact, is something that we're looking at the moment. So I think there's some really good prospects for actually then being able to regenerate some of the uranium from these in situ formed layered double hydroxides. Okay, I'd like to move on now to the last example I've got, which is the formation of a potential repository material from layered double hydroxides. And so the question we posed to ourselves there, was there a way to further concentrate and stabilize these contaminants in this quite enriched, I use enriched not in an isotopic sense, but enriched in terms of an element sense, layered double hydroxide? And we did a lot of work around this, and the answer was either selective mineral addition, or in the simplest way, just controlled calcination leading to the amorphization of the layered double hydroxide. Now, what that forms, as you'll see in a few moments, is a series of known host minerals and also novel secondary mineral assemblages. So what happens when you heat up the layered double hydroxide that we had from the Beverley mine? Well, we've got here there on the right, heating anywhere up from 0 to 1,000 degrees. And we looked at differential thermal analysis and thermogravimetric analysis, and that was used to examine mass loss, heat flow, and 2 of the evolved gases, which was water and CO2. So if you look at the first line there, the TG, which is the mass in percent, that's the blue line. So we obviously start off at 100% there. And as we heat it up to 1,000 degrees, we end up going down to about 65%. So just simply heating the layered double hydroxide, you can lose about 1/3 of the mass. So that's just a really neat way if you want to reduce the final mass of the LDH, even though it's really, really small to start with, you can still reduce it by about 1/3 just by heating it up. And you probably don't have to go above about 700 degrees to do that. Now, if you follow the green line, which is the water, and you can see as you heat, you start to get a net loss of water. That green line starts to increase up to about 100 and 200 degrees. And that is the loss of the waters of hydration, as you may have seen earlier, that are present in the interlayers of the layered double hydroxide. But then when you start to heat it up further, this sample, between about 400 and about 600 or so degrees, you then actually have a dehydroxylation reaction. So you remember the metal layers, there are metal hydroxide layers. So you actually start to dehydroxylate those. So you then start to lose more waters and you start to form what's known as a mixed metal oxide. But coincident with that loss of water that peaks around about, say, high 400, almost 500 degrees, you also have loss of CO2. And that CO2 was the carbonate and bicarbonate that was originally present as anions in the layered double hydroxides. And then above about, say, 600 or 700 degrees, not much more happens. But you've pretty much decomposed everything up above around 600 degrees in terms of loss of water, loss of CO2, and conversion of the layered double hydroxide to a mixed metal oxide. So what does that mean in terms of the mineralogy? We've done a thermal X-ray diffraction analysis, and we go from about 20 to about 1,320 degrees. And we've got the layered double hydroxide, and just for your note, the periclase here is known as PE, spinel, SP, monticellite, MT, and the platinum is actually the platinum heating stage. And that's those 2 bright red lines that go from the bottom to the top of the diagram. So in that diagram, it's basically just a heat map, blue, cold, red, hot. You've got temperature, as I said, from 20 to 1,320 degrees, and you've got the angle, the 2 theta degrees in the X-ray diffraction. So if we have a look at the LDH first, the one between about 10 and 15 degrees, as you heat the layered double hydroxide, you get up to about 200 degrees, as you remember from the previous diagram, and you start to get dehydration. Once you get dehydration, you start to move to a smaller interlayer space or a higher 2 theta degrees. So you're effectively just clamping down these layered double hydroxide interlayers as you lose the water. Then as you move above about 200 degrees, not a lot happens, but then once you get to about 500, 600, 700 degrees, you can see some faint green images or faint green patterns on the XRD trace, and those correspond, you're starting to form those mixed metal oxide layers as you've lost your water through dehydroxylation and CO2 from your interlayer carbonate bicarbonate. And then again, not a lot happens until you start to get up to about 900 or 1,000 degrees. And so what you then initiated is recrystallization of this layered double hydroxide. We start to see periclase forming, periclase being a magnesium oxide, so that's the first phase to form. But after that, we then start to see monticellite forming, monticellite being an olivine mineral, and also spinel, spinel being an oxide mineral, in this case, an iron alumina oxide. So above 1,000 degrees, you get lots of these recrystallization reactions occurring. And this is where the really interesting stuff starts. So if we have a look at these post-calcination mineral phases, so this is just an SEM, on the left is just a grayscale, and on the right is a false color image. And we'll go to the false color image, concentrate on that one on the right. And so you've got spinel in green. You can see a really lovely hexagonal spinel crystal there in the top right-hand side. You've got periclase in the purple. And then what we saw was a really interesting uranium rare earth phase in the red that predominantly occurs along the grain boundaries. We also have pliniusite, which is a vanadium-rich apatite, which we haven't shown there. But what we're actually thinking here, as we'll show later, this is due to what's known as late-stage cooling and incompatible element exsolution. So while this sample is up at, say, 1,000 to 1,300 degrees, you can accommodate the uranium and the rare earth, the larger ions within these open crystal structures. But as you start to cool, the crystal structures start to close down. Uranium and rare earths have got nowhere to go, so they are exolved from these crystal structures, and then they end up as interlayer phases that occur between these other major mineral components that we have in this calcined layered double hydroxide. So now if we look at the compositions, and I won't labour this too much, it's really just looking at the first column there, the uranium rare earth oxide. That contains around about 71% U3O8. It contains pretty much all of the thorium, all of the lead-210, so it's got all of the radionuclides pretty much associated with it. It's got all of the rare earths, the total rare earth oxides there of 19.3%, and it's got a few other minor major and trace elements associated with it. The apatite, which is a vanadium apatite, all I really want to highlight here is that it contains about 3% rare earth oxides. But the important thing here is it contains about almost 3% strontium. And strontium is important if you're looking at nuclear waste, because strontium-90 is a fission product of the nuclear energy cycle. The other important thing to say here is that now with this uranium at around about, or U3O8 at around about 71%, we've got around about a 50,000 concentration factor from that original barren lixiviant that we started with. So an enormous concentration factor. The only other thing I'd say as well, the rare earths are important when you look at them as analogues for actinides, the neptunium, plutonium, and the like, in +2 to +4 oxidation states. So what we've really got in the uranium rare earth oxide, we've got the uranium, we've got the daughter radionuclides, and then we've potentially also then got a whole lot of actinides that we can accommodate into the structure. But then in the apatite, we also mop up most of the strontium, and by implication strontium-90. The monticellite, the spinel, and the periclase, if you just look at the top of that diagram, they pretty much contain no uranium, no thorium, no lead-210, and only a tiny amount of rare earths. So all of the other major phases, which constitute greater than 99.9% of the sample, are effectively clean. So we've concentrated everything into 0.1 of this sample. Okay, if we have a look at the atom probe analysis now that we conducted on this sample following calcination, this atom probe analysis, this is 34 million atoms in these individual images, and this is a 3D reconstruction. The spike that you see here is around about 300 nanometers long. What we can show, and I won't go into great detail, but we've got an interface there where we've mapped across that top right-hand image. And so we can see uranium declining across that interface. We can also see in the blue cerium, one of the rare earths, declining across that interface. And we can see as we cross to the other side, we've got iron increasing, which tells us that we've gone into a spinel phase. And the really interesting thing about this as well, you can see a little blip just above 0 there that is actually beryllium. And just one moment. And if we look at that, we can actually see beryllium here in the purple in this image. If this will play for me, it's probably not going to play now, unfortunately. No, it won't, but so be it. The beryllium actually forms an interface, just an atom-thick interface between that and where we see the precipitation of these uranium phases. It's just a really interesting little outcome from the work. Oh, it is now playing. There we go. So you can see that atom-thick beryllium interface that actually forms between the uranium, which is that red and orange phase, and I'll play it just once more. Oh no, I'll go on to the next slide. Okay. So finally, I just want to have a look at the radionuclide, a summary of the capture and containment process. So we've got the layered double hydroxide there on the left. We get the thermal treatment and recrystallization into the spinel and the periclase upon cooling. We then have the exsolution of the pliniusite or apatite phase, and also the uranium mineral occurring at the grain boundaries. So this is a really neat little process that has allowed, as I said, to give us enormous concentration factors of uranium and rare earths, and by implication, also a lot of actinides that may be present, for instance, in a nuclear waste. Okay, so what is the usefulness or the utility of this layered double hydroxide capture and recrystallization mechanism? Well, with the layered double hydroxide, we have high radionuclide contaminant capacity, we have ease of separation, and we have single recrystallization step. We have a processing pathway that doesn't increase the final waste form mass, and it can be used for other radionuclide contaminated waters. The mineralogy is really important. Spinel, periclase, and olivine, that is a lower mantle mineral assemblage. So it is high pressure, temperature tolerant. And think about that in terms of a nuclear waste repository. Fortuitously, the mineralogy is also inherently tolerant to radiation damage. It has high temperature thermal stability, a low volumetric expansion, and these are essential prerequisites for a nuclear repository material. Okay, in summary, I'd just like to move on now to talk a little bit about the NAWI project in terms of future research and activities. So as I said at the top of the presentation, our NAWI project is entitled Ultra High Pressure CSIRO with Virtual Curtain, the name we've used for this in situ layered double hydroxide technology, to achieve minimum liquid discharge. And so this addresses one of the major techno-economic challenges of treating difficult waters with high scaling potentials where we want to achieve zero liquid discharge. So the project really involves the integration of DuPont's CSIRO with our layered double hydroxide process with the goal of maximizing water recovery, because with removal of foulants, as well as things like total hardness, we can then minimize, or we're going to actually look to minimize the effect of these foulants to allow RO to actually operate at its true osmotic pressure limit. So a major outcome from that we're hoping is for a substantial reduction in both CapEx and OpEx, leading to minimal liquid discharge. Some of the other options will be to look at, for instance, in the US Permian Basin, to look at the removal of radium and radionuclides and other foulants from produced waters. And some of the other things we'll look at is we could potentially also partner or work with other NAWI projects where this technology may prove useful to them. But elsewhere in the US, we could look at acid mine drainage, as I discussed earlier on with the Balgammon site here in Australia, but also other surface and groundwater remediation for difficult waters. But also we're looking at or for US technology and licensing partnerships. And so with that, I'd like to acknowledge a whole lot of people here. They know who they are. I won't read them out individually, but just the images on the right there for those that have anything to do with the uranium industry. It's very important to know the difference between yellow cake and yellow cake.
So that's the yellow cake we were supposed to find in Iraq. Thank you, Grant.
That is. And finally, just any questions? And I've got my partner in crime here, the largest kangaroo ever seen, over 200 pounds, recently deceased in Australia. And that's a fair set of muscles on him. That's all I can say.
Is that a real picture?
That is a real picture. He did that.
That dude is ripped, man. Wow.
He's no longer with us, but and that's a good thing.
I'll say. Grant, thank you so much. That was fascinating. And I will first of all admit, NAWI audience, that as a mineralogist, I found this particularly lovely, Grant, for you to walk through some really interesting mineralogy and trace mineralogy. Now, I know that we have questions that can come in on the chat, so I encourage you all to put in some questions, but I have a whole bunch, and I'm going to start right now, Grant. So I guess here's one question I have at the end. You're sort of teasing us, but I'll go in reverse order. Just describe visually what a virtual curtain pre-treatment system would look like. So you have feed pumps, and like how big would the vessel be to settle, and sort of what's the hydraulic residence time as a function of the treatment time. Just give us a sense for what it looks like.
Okay. Well, we've already got the two there. I'll leave the in situ one to the side where we look at a mine pit, because obviously that's just adding chemicals to a mine pit, letting it form and letting it settle. But in the case, for instance, of the Chinese example, where we treated the 7 gigalitres a year of groundwater, we were removing silica and total hardness. In that case, we just had the pipe that was running in from the groundwater pipe that was running in. We retrofitted a couple of T-pieces into that. Those T-pieces were attached to tanks. Those tanks were stirred tanks where we might have reagent 1 and reagent 2. So it's a simple pump and metering system. It's really, really low tech. I mean, this is one of the wonderful things is that it is not big CapEx costs. It is pumps. It is a little bit of a control system, obviously, just to control the metering on the pumps. We have a final pH feedback loop because obviously we want to have our final pH there. On occasions, we'll have a flocculant tank also where we want to add a flocculant. In the Chinese case, they used a sand depth filter, which is about as low tech as known to man. But we've also used dissolved air flotation, where we actually pump out the effluent after it's formed in pipe. And again, the pipe, there's no mixing of the pipe as such. Use static mixers just to create turbulence within the pipe. The formation is spontaneous. So again, there's no further mixing or nothing else to do in the pipe. And dissolved air flotation, I wish I'd included a picture. I've got a lovely picture of some of the DAF work that we've done. But typically you're floating off less than 1% solids in terms of the volume of the water. So you can recover 99% of the underflow. And there you have almost like that gel you saw in that picture of the Balgammon mine. You can form almost a gel that you can skim off, and then that gel can be dried or disposed of or recovered, for instance, if you wanted to recover metal values out of it. So the CapEx side is unbelievably cheap and unbelievably simple, I guess is probably the quick answer.
Cool. Another question I had, swinging the pH is sort of the name of the game here. So that would appear to be a primary cost driver associated with this. So how do you look at, the methods to swing the pH? Is it simply, addition of sodium hydroxide? Do you do in situ generation of anything? When does it make sense? Do you need trucks of sodium hydroxide to come in on site? Just tell us a little bit about the physical mechanism of the pH swing.
Okay. In some cases, it's obviously when you're dealing with acid water, yes, there is a lot of sodium hydroxide to be added because you do need to get up to pH 8 or 9 or 10, depending on what you're forming. And so that is just a given, and you live with that. Obviously, in some of these other groundwaters where we were starting with pH of 7s and 8s, the pH increase is really, really marginal, so you're only using a very small amount. What I've always had in my mind's eye is that because we actually do get such a clean, and I use that word in inverted commas, but clean solute that you saw, for instance, in the Balgammon pit, that was very easy to RO, the brine that you actually got there is then set up beautifully for electrolysis to form, for instance, sodium hydroxide and where you've got a lot of sulfuric acid. So I've always had in my mind's eye that we could actually close the loop here and be a really efficient operation, that sodium hydroxide could then go back into the process at the start.
Yeah.
And for instance, at a mine site or even anywhere else, you could form your sulfuric acid that you could sell or use in another process. So yeah. I think there's real opportunities there if you wanted to look to close the loop. Now that would obviously rely on a low cost power source, electricity source. But I know in Australia, I'm sure in some parts of the US, there's major mines here putting in literally acres and acres of solar panels as far as the eye can see. And I've seen these in China as well. I've driven for kilometers on a road in China where all you can see is solar panels.
Wow.
So there's that sort of way also to look at closing the loop in terms of your power requirement.
Yeah, very good. Well, so one other question I had is, it's very interesting because now with the ability to kind of selectively precipitate and concentrate some of these metals, I was curious, Grant, if there, now with this sort of platform technology, are there any waste streams that we currently throw away or don't consider that with LDH treatment could actually be ore deposits, economically recoverable things? Are there any particular industrial settings where you think this might make sense?
I'll probably go to mining first because that's the easy one. Yeah. Anywhere you treat with lime. If you treat with lime, you form gypsum and you generally throw that in a tailings dam and you've lost all your metals. Whereas in LDH in a mining setting, as you see, we can get enormous concentration factors. In this one case, I show twice the actual ore grade in the mine pretty much. Yeah. You could put that back through the metallurgical circuit. And so you've done a couple of things there. One, you've partially offset the cost of your treatment by the metals you recover, but also your final repository, you've depleted those of metals and other contaminants as well. So anything you've got left over is a heck of a lot cleaner than, for instance, in terms of the mass of something you might have treated with gypsum.
Right.
So that's one part of it. In industrial settings, yes, absolutely. We've looked at, and this project didn't proceed, but actually looking at recovering high purity silica from a semiconductor plant. We could use this to recover high purity silica. This is fouling their RO membranes, as you might expect. They last about a day, or it's almost like that. We could use it to do that. The other one is just in metals plant. We use metals, so I'm thinking plants where you're electroplating and things like that, where you've got metals coming out, chrome and the like. We actually want to recover that chromium rather than going to waste or whatever. Again, that's somewhere where you could look at doing that and trying to close the loop. So there's any number of in inverted commas, metal type plants where this could be potentially applied. Yeah.
Okay, very good, Grant. I was looking at your spectrum of kind of concentration factor line. I didn't see selenium anywhere. Where's selenium fall?
Selenium's fairly low down. I think we only got a depletion of about 2 times, 3 times, I think probably over there. Selenium is traditionally a difficult one, as probably we all know, because it's outcompeted by just about everything. And you're not the first person to ask me, does it take out selenium? Yeah. And I say, yes, it can, but it depends. And the depends is if you've got lots of other competitive anions, well, the answer is probably not very well. Yeah. I would love to be able to say to you, yes, because that's a $1 trillion market just taking out selenium immediately. But unfortunately, no, it doesn't do everything. It's not kryptonite. It's sort of, but it does a lot of things.
Great. Well, look, we are at the bottom of our hour, sir. So I'm going to say thank you so much, Grant, for a fascinating presentation. We look forward to seeing Virtual Curtain do her dance of the 7 softening veils at some point in the future at NAWI. And everybody here on the NAWI channel, thank you again for attending. This recording will be available on NAWI Alliance HiveBright site. And Grant, once again, thank you for getting up so early in the morning, having a triple espresso and starting tomorrow with us. Appreciate it very much.
Okay, my pleasure. Thank you very much.
Bye-bye, everybody.
Bye-bye.